Welcome back everyone. In the last lecture we had seen the idea of observability and observers. We came up with the Leuenberger observer that will help us to estimate the states of the system. The question that we left in the last lecture was that how do we find out that L matrix that will govern the rate at which the errors will go to 0, the error being the difference between the actual state and the estimated state. Today we will look into that. So, given a system of this form, this is the actual system that you have, we came up with this Leuenberger observer and the dynamics of the error was given by this E dot equal to A minus LC ET. Remember, the control law that we are putting into the system is U equal to minus Kx hat plus NR. Now, remember that this x hat is not exactly the x that we had talked about. When we were talking about state feedback, our control law was of the form U equal to minus Kx plus NR. Now, we have changed the control law from x to x hat. Then the question is, will whatever we have been doing work still? I mean, the idea is that if I use this control law, will I be able to place the eigenvalues of the closed loop system wherever we desire? Let us look at that. What happens if we plug this control law into the plant? So, U will get replaced by this expression and then we are left with Ax minus Bkx hat plus B and R. Now, this equation can be rewritten in this form where basically what I have done is I have added Bk xt to it and subtracted Bk xt from it, okay, and while doing so what I am doing is, you see, I can take x common from here and I get A minus Bkx, and from here also I can take Bk common, I get x minus x hat here, okay. This is the expression that I get, and then you see this expression is nothing but Et, and therefore x dot can be written down as A minus Bkx plus Bk into Et plus B and R. So, this is the first differential equation. This is the differential equation that the actual plant is following now, okay, and the error dynamics follows this differential equation E dot equal to A minus LC Et. Now, notice what is the good thing about this is that you can design a K such that the eigenvalues of A minus Bk can be placed wherever you want to, okay, and this actually is what we were doing when we were taking U equal to minus Kx plus NR. So, this K helps you to place the eigenvalues of the actual system at a point where you desire. Why was that important? Because doing that you were controlling the rate at which the states will be evolving, because the eigenvalues governs the rate at which the states evolve, and I can design a L here separately, okay, which will help me to come up with a observer such that the x and x hat converges to each other as fast as we want. Okay. So, this is what is known as separation principle. In other words, I can separately design the controller and I can separately design the observer. Although it looks like A's eigenvalues are getting affected, but here A minus Bk is a different system and A minus Lc is a different system. These same equations can also be rewritten in this way. Instead of E dot, if I replace E dot by x hat dot, I will get something like that. See, x hat dot here is Ax the hat plus Bu plus this, okay, this is your y, this is your y hat, and from here you can see that when I place in place of U, when I place this control law, I will get an expression of this form, and from this expression you can see I can take A minus Bk x hat as common, and then from here I can take A minus Bk minus Lc x hat here, and then from this part I have LC of x plus Bn r. So, these equations can be rewritten in this form. You see, LC of x A minus LC minus Bk x hat plus Bn r. Okay. So, for for this entire system, this is in this system what we are doing is that the actual plant was this. We used a control law of this form. Now, this control law is based on the estimated states, right, and that is why this control law, this controller is also called an observer based controller, because the controller depends on the estimated states from the observer. Okay. So, this control law is an observer based controller. So, if I use an observer based controller of this form, then the dynamics of the entire plant, basically plant and the observer taken together, is given by these equations, where the first equation, differential equation, takes care of the states of the actual plant, and the second differential equation here takes care of the estimated states or the dynamics of the estimated states. So, if you remember, when we had designed the observer, this brown part here was the observer for you. Now, what we are doing is that we are using a controller of the form, an observer based controller of the form u equal to minus k hat plus n r, and therefore, this is how we are actually connecting the system. We are tapping into x hat here, which we can do because this copy has been created by us. We tap into that, and then minus of k x hat, this you can feed it in here, and is something you can come up with. Here we will give a reference trajectory. So, the reference trajectory gets multiplied with n, and you can see that this is the observer based controller that we were talking about. Now, in this setup, remember that the states are no longer the original states, but the estimated states, and I can design this k and this L separately. I can come up with an L and I can come up with an k separately, and I can design both this system separately. I can design the controller separately, I can design the observer separately, and this is what is known as separation principle. Okay. Now, the question would be, fine, we already know how to find out the k. Finding out the k remains exactly similar. The method of finding out the value of k remains exactly similar, because you can still see that k is nothing. So, at the end, if I apply this control law, if I apply the observer based controller also, it is A minus Bk, which is the system matrix that we have, right. So, finding out the value of k remains similar to what we have discussed earlier, okay, in the last in the lectures before this, okay. But now we will have to discuss how do we find out this value of L, okay, and it turns out the methods are quite similar to what we did for the controller design case, okay, and that is because of this idea called duality. Now, what is duality? Now, what is duality? Duality says this: suppose you have x dot equal to x plus bu and y equal to cx plus du, then AB is controllable if and only if A transpose B transpose is observable, and AC is observable if and only if A transpose C transpose is controllable. Why is this true? So, suppose let me just take one example, one of this statement and try to prove it. You can try to prove the other statement on your own. So, if I say the only if side, that is, suppose AB is controllable, and we have to prove that A transpose B transpose is observable. So, since AB is controllable, we know that rank of B AB to A to the power n minus 1 B must be equal to n. Now, I can take a transpose here. Even if I take a transpose, the rank does not change, because we know that the rank of a matrix P and its transpose are the same, right. So, which means that I can write it like this. In other words, if I take a transpose of this matrix, the transpose of this matrix will come out to be B transpose, A transpose, and this. And notice this looks like this. If I can consider as C, this is another C, this is another A. So, this looks like C, CA, CA square, CA to the power of n minus 1 B, n minus 1. So, this that means B transpose is your new C, A transpose is your new A. So, A transpose B transpose must be observable. In the other way around, if I consider that A transpose B transpose is observable, then see rank of this must be equal to n. In other words, the transpose rank of transpose of this matrix must be n, and in other words rank of B A B, the controllability matrix must be n, and which means A B is controllable. That means if A B is controllable, A transpose B transpose is observable. In the same way, if A C is observable, A transpose C transpose is controllable. Now, how does it help us? Now, notice that if that is what duality is, basically AB controllability implies that A transpose B transpose is observable and vice versa. Okay. Now, how does it help us? Now, notice that we know that if AC is observable, then A transpose C transpose is controllable, right? And if A transpose C transpose is controllable, we have already seen that the controllability Gramian corresponding to A transpose C transpose must be then non-singular, right. Remember, if A B is controllable, then we used to write that e to the power of A tau B transpose e to the power of A transpose tau d tau integration from 0 to t was always non-singular. This we used to do, right. You can go back to the lectures and check. Okay. So, that is what I am doing here also. So, in place of A I am just writing A transpose, in place of B I am writing C transpose, and this is what I get. Again, the controllability matrix also changes now. So, the controllability matrix will be, instead of B I can take C transpose. So, again A B is A transpose C transpose and so on, and the rank of this matrix must be equal to n. And again the PBH states the rank of A transpose minus lambda I C transpose must be n. Again here is your A, this is your new B, right. So, all this we had seen, only thing now what I am doing is I am replacing A and B with A transpose and C transpose. Now, see omega naught is this is non-singular, is equivalent to omega naught transpose being non-singular, right. Similarly, this same this rank of this being equal to n is equivalent to the transpose of this also, the rank being n. And similarly, from here rank of A transpose minus lambda I C transpose being equal to n is equivalent to the rank transpose equal to n. The transpose of this matrix says rank will also remain equal to n, and that is why we can again go ahead and if I take the transposes, this can be written down in this way, right. And this is what are the equivalent statements for observability. See, I do not even have to prove these statements, because by duality itself I can directly say that these statements will be true. So, a system is said to be observable if and only if the observability Gramian, this is now called the observability Gramian, the observability Gramian of the matrix is non-singular, the observability matrix has full rank, or the rank of A minus lambda I C is equal to n. Here they are being stacked on the top of each other. So, you can see that these exactly similar to controllability, we have these equivalent statements. Remember, this is called observability Gramian. Okay. Now, how does that help us again? Remember the question that we were asking. We were asking how do I find out that L matrix that we want. Let us take an example and try to design an observer based controller for that system. Basically, when I say that we will try to design an observer based controller, I mean that first we will design the controller, that means I will find out the K matrix. Once I find out the K matrix, I will design the observer, because the observer, designing the observer means finding out that L matrix. I will need to find out that L matrix. Why? Because if I find out that L matrix, I can create a Eulenberger observer using which I can estimate the states, and using that states I can feed it back into the system using the control law U equal to minus k x hat plus nr. So, let us take this example, and in this example the entire recipe of finding out those observer based controllers will be clear hopefully. So, the system that we are starting off with is this: x dot equal to ax plus bu, y is this, and we are asking the question, design an observer based controller such that the eigenvalues of the observer are at -4 and the eigenvalues of the controller are at minus 12 and minus 4. Okay. So, you can see I am designing two systems, one is an observer and one is a controller. Okay. The observer will help me to get XAT and the controller will then use that XAT to implement this control law. Okay. Of course, n is not being asked here because I have not told what will be the steady state value of the output. Okay. This information is not given to you. So, in this example at least I am not trying to implement this control law. So, I am implementing only u equal to minus k XAT. Great. So, how do we do this? So, the first thing always to check is that first of all, if I have to design a controller, I know that the system has to be controllable. If it is not controllable, I need to take it to controllability canonical form, and then I have to check that the uncontrollable eigenvalues I will not be able to change. All these things you have to check, right. Of course, in this example I have taken a case when we will have a controllable system, B is 1 1 here and AB will come out to be 1 and minus of 11. So, this is a rank 2 matrix. So, this is a controllable system. Whatever the observability, because if we have to design an observer, the system better be observable. So, we will have to find out C, CA. So, what is C here? What is C here? C is 1 2 and what is CA here? CA will be equal to minus 9 and then minus 12. So, this is again a rank 2 matrix. So, this system is both observable and controllable. So, that means I can directly design an observer and I can directly design a controller as well. So, let us first go ahead and convert the problem to a controller design problem. So, we will design the observer first. Okay. So, you can do the other way around also first, but here I am just designing the observer first. So, to design the observer, I will convert this problem into a controller design problem. So, what do I mean by that? Remember, if I have to design the observer, remember what I am trying to do? I am trying to place the eigenvalues of this A minus LC at minus 4 and minus 4. This is what I am trying to do. So, I am trying to find out an L such that the eigenvalues of this is at minus 4 minus 4. But notice that eigenvalues of A minus LC and the eigenvalues of this are the same, right, which means I can go ahead and rewrite this as A transpose, this becomes C transpose L transpose. This is again by duality we will use C. Now, I can consider this to be your new A. So, this is your new A and this can be considered to be a new B and this you can think of K new. So, I am actually finding out a K new for A, so to place the eigenvalues of A new minus B new K at minus 4 minus 4. So, this is what duality is and we know how to do that already. So, you see A new becomes A transpose, this is your A new, and B new becomes C transpose, which is 1 2, and I want to place the eigenvalues of this new system A new comma B new. Okay, this is like a controller design problem now. So, I have to place the eigenvalues of this at minus 4 minus 4, which we know how to do using Ackermann's formula, right. If you remember the Ackermann's formula, using the Ackermann's formula I can easily do this because the Ackermann's formula was something like this, right. So, I have to use the Ackermann's formula to get to the solution get to the gain. So, I will use this formula. So, to find this formula, you see desired characteristic polynomial is s plus 4 whole square, then in place of s I can put A new and then this will become A new minus 4 I whole square, which comes out to be this, and then K new will be 0 1 controllability matrix inverse, then we have x desired A new and from here this will be the K new that I get. But this K new is nothing but L transpose, right. So, L will be nothing but K new transpose. So, that is 1 by 3 minus 25 17. So, this is the L matrix that you were looking for. This L matrix will place the observer eigenvalues at minus 4 minus 4. See, the procedure is exactly similar to what we did for controller design. Only thing is that now we have to transpose and make the observer design problem into a controller design problem. Now, we will place the, okay, by the way this is the, this is the observer that we had designed, L has been replaced by this now. So, this is the observer equation. Okay. Now, we will design the controller. So, for the controller, what is our A and B matrix are this, Okay, this we already know. So, this is our A and B matrix. I want to place the eigenvalues at -12 and -4, and you can see by Ackermann's formula the desired characteristic polynomial is s plus 4 into s plus 12. Then in place of s I am putting A, and this is the x desired A that I get. And now using Ackermann's formula, if you go ahead and plug it in, 10 and 1 will be your answer. So, your control law is this. Okay, you can use this R. Even if you do not use this R, it's fine, because we have not been told what our steady state output would be. So, as a whole, how will your observer based controller look like? This is the setup, right? Here this is your A, this is your B, this is your C. Here you can see this is A, this is B, this is C. Then I have designed the observer using this L matrix, and this is my K matrix or minus K matrix here. Okay. So, this is how the actual system will look like. Since I have not been told what my steady state output would be, I can choose this to be 0 also. Okay. But if you have some value, then you can go ahead and choose that n value there. Let us try to simulate this system and see. So, you can see that these are my A, B, C, D matrix, okay, and then I have taken my K to be this, L to be this, and here although I have not taken, there was no objective for n there, because the steady state value was not given. So, we can actually go ahead and take an n value, we can actually go ahead and take a target reference also. So, I am taking the target reference to be 1.5. I mean, although this question did not ask for that, but if you want, you can do that. You can find out the n also. Let me try to simulate this. So, first we will, you see simulation A, this part actually simulates the actual system. The actual system actually was an unstable system to start off with, because one of its eigenvalue was at +1, okay, and then we have used the controller matrix K to stabilize the system. We change the eigenvalues to -12, -4, so that the system becomes stable, and to get the control law we needed x hat, and that x hat was being created using the observer. Okay. This is the combined dynamics of the system. This entire dynamics is the combined dynamics of the system, which I had already written x and x hat dot. This is the combined dynamics. So, let me see if I run it, what do I get? You can see this is the system I get. The first, these are the two states, the states without any feedback. You can see without any feedback the system is unstable, because the states are just becoming unbounded. Now, once I have given a feedback, you can see that the states are now, these are x1 and x2 are your actual states, and these are your actual state, and the observer is estimating these states. The dotted lines here are the observer's estimated states. These are the states that I have used to feedback into the system using u minus kx hat plus nr. So, those are the estimated states, and the estimated states you can see are actually becoming equal or becoming closer and closer to the actual states. Okay. And then these states help us to get to get to a final system output of this form. You can see that the final output has now reached 1.5. You can change this 1.5 to, you can change this 1.5 to something else also. Let me just change it to say 1.3. So, if you change it to 1.3, you will see that the output will also go to 1.3. Okay, the output here is at 1.3. So, this way this is how you can actually go ahead and design the entire system. Okay. So, this is the procedure to design both observer and controller together. Okay. Separately we are designing them. This is what the separation principle is all about. Okay. We design the controller using whatever methods that we have talked about earlier, and then we design the observer also. Only thing in observer is that we convert the problem into a controller design problem, and then we design the observer. Okay. And also, if you have a final steady state value of the output to reach, then you have to carefully select your n, and we had talked about how to select the n also, that feed forward control. Using that n, you can reach to the state that you want to. So, this brings us to the end of how to design controllers and observers for a system, okay. And by this hopefully you understand how we can implement a state feedback controller using observers. In the next lecture, we dive a bit further and look into the decomposition of states space. Thank you.